So, good evening, everyone. Today, this is my last session of this course. So, today I'm gonna, all you know, my name is Chanda Devnath. I have got my PMRF this last year in December. So, as a TAship for my this fellow PMRF, I am doing this course for you guys. So the course instructor is Professor Rajashri Shamanta. So I am trying to elaborate or introduce some more reactions based on this reactive intermediate carbenes and nitrates. So let's start. Today is the last session. So I will try to finish today. So let's talk about nitranes. So in the last session, I already have started about something regarding the nitranes. So nitranes are the nitrogen analogues of carbenes, as the carbenes can have both the singlet and triplet states, but in case of nitranes, the triplet state is usually the ground state. So how these nitranes can be generated? The most common method is the thermolysis or the photolysis of azides. So here you can see. So this is the thermolysis or photolysis. By the application of heat or light, this N2 will get removed and we will get the nitrene. So the characteristic reactions of nitranes are, one is the migration. So the adjacent group, on the adjacent carbon atom can migrate to this nitrene nitrogen atom. So it is one of the type of reaction of nitranes. Another one is the aryl nitranes undergoes rearrangement. So in case of aryl nitrene especially, there is a chance of rearrangement. So there will be a bond shifting from here to here. Then the nucleophile will attack and will get a rearranged product. So a few intramolecular insertion reaction can also be possible. So here you can see this this after the N2 elimination, after when this N2 gets removed from the system, we'll get nitrene, and this nitrene will insert into this adjacent CH bond. This nitrogen will insert into this adjacent CH bond. So this all I have taught in the last session already. So let's start with some new reactions. So what is the nitranes that most consistently give addition and insertion reaction are the carbo-alkoxy nitranes generated from the alkyl azido format. So you can see this type of alkyl azido format can undergo thermolysis or photolysis to give this type of nitranes. So next is this intermediate. This type of nitrene intermediate can undergo addition reaction with alkenes and aromatic compound, and also insertion reaction with the saturated hydrocarbon. So if it is alkene or any aromatic compound, it undergoes addition reaction similar to the carbene. I have already taught you about that when this carbene, there is a alkene group and there is a carbene, and there is a carbene, so it get insert into that alkene. It get insert into that alkene. So this I have already explained. So in case of nitrene also, if it is alkene or any aromatic compound, it insert into that. See, this is alkene. So nitrene had been inserted into the double bond. In case of aryl, it first inserted into the one of the double bond, then rearrangement occur, like as similar as to the kind of in case of carbene. So this type of reaction you have already seen. First nitrene will insert into the one of the double bond of benzene. Nitrene will insert into one of the double bond of benzene, and then a rearrangement will occur. This will go here, this will go here, and we will get this compound. So this type of reaction I have already taught in case of carbene. So a similar kind of reaction will happen in case of nitrene also. And when it is saturated hydrocarbon, when there is no double bond is there, so it will just insert into the one of the CH bond. So there is lots of CH bond, this will insert into one of the CH bond. So the next is sulfonyl nitrines are formed by the thermal decomposition of the sulfonyl azides. So here you can see this type of sulfonyl nitrine can be formed in the similar way from sulfonyl azide. If there is a N2, this N2 gets removed and we will get this type of sulfonyl nitrine. Understood? We will get this type of sulfonyl nitrine, and when we are adding some aromatic compound, it will insert into that one of the double bond. But there is a difference in case of normal carbonyl nitrine and sulfonyl nitrine is that in case of this type of nitrine, similar to carbene atom, similar to carbene, there will be a rearrangement. But in case of such a rearrangement, there will be a ring expansion. See, here is a ring expansion is happening. But in case of sulfonyl nitrine, there is the rearrangement occurring in such a way that it seems like the sulfonyl nitrine has just been inserted into one of the CH bond. But here rearrangement occurs in like this way. It come here. Yeah. So here rearrangement occurs in such a way. So by seeing the product, we may assume that it has been inserted into the CH bond, but it goes through a addition. But after the rearrangement, the product is similar to as the insertion product. Next, let's talk about some name reaction involving nitrene. So first, the name reaction is the Carbenes rearrangement. This is one of the most useful reaction involving nitrene as an intermediate. This reaction has the same relationship to the acyl nitrene intermediate that the Wolff rearrangement does to the acyl carbene. You all have remembered me about the Wolff rearrangement. I have taught in maybe in the first or second class that when a diazomethane group is added to a acyl chloride, you will get this type of acyl azide, and this after the removal of the N2 atom, we will get this type of carbene, and this carbene undergoes a rearrangement giving us this type of intermediate ketene like this is called ketene. This type of ketene like intermediate, when we are adding any solvent like alcohol or water, we'll get this type of acid or ester. Okay, this I have taught already. So similarly, in case of Carbenes rearrangement, instead of diazomethane, we are adding N3. If we react this one, with N3 minus, it will attack here, and Cl minus will get removed, and we will get this type of product. And this one undergoes a rearrangement where the adjacent R group will shift to this nitrene atom, and N2 will get removed from the system and giving us this type of intermediate. This is called ketene. See the difference. There is a CH double bond O, but in case of CH, instead of CH there is a nitrogen. So this is called isocyanate. This is called isocyanate. This is called isocyanate. So instead of ketene, we will get isocyanate intermediate, and in the similar way, when you are adding water, you will get acid. and if we add any kind of alcohol or something, we will get ester. But in case of water, when you get acid, there is a chance of the elimination of carbon dioxide, which will leads to the formation of amine. This is the one of the extended feature of in case of nitrene, that here is a chance of elimination of carbon dioxide, which will give us this type of amine compound. Understood, everyone? So what is the difference between the wolf and Cartiers? That is, in case of wolf, we are getting ketene intermediate after the migration of the R group, but in case of Cartiers, after the migration of the R group, we are getting a isocyanate intermediate. And when we are adding any solvent like water or alcohol, we will get this type of ester or acid. When it is acid, there is a removal of carbon dioxide, leading us to the amine. Okay. So let's talk about some properties. So the initial product is an isocyanate. I have already taught you that the intermediate formed here is called isocyanate. So the initial product is isocyanate, because this can be, I am already telling that it is intermediate. So intermediate can be isolated, so that we can consider this as a product, because we can isolate that. So there is a difference. You all have known maybe that there is a difference between intermediate and transition state. That transition, in case of transition, we can't isolate the product. We just imagining that this has been formed in case of reaction, in somewhere in the reaction, and it from that we are getting the product. But in case of intermediate, there is a advantage that we can isolate that one, and this will give us idea that how the reaction is happening, because we can isolate the intermediate, and that will convert it into the product. So the initial product is an isocyanate, which can be isolated or trapped by a nucleophilic solvent. As I was telling, nucleophilic solvent like water, alcohol, if we add into that isocyanate, we can trap the isocyanate, leading us to give a acid or a ester. So this reaction is concerted, and the migration accompanies with the loss of nitrogen atom. See, the migration this is the concerted reaction. See, this the migration and this elimination is both are happening in a single step. And this migration happening with the loss of a N2 atom. And I have already taught you that the elimination of nitrogen is always favorable, because nitrogen, see there is a triple bond. This is such a strong bond, so elimination of nitrogen is always favorable. And the migrating group retains its stereochemistry. So when this R group will migrate from this carbon to this nitrogen atom, the stereochemistry of the R group will be retained. See, here it is only as a R group, so you can't understand. But if it is a chiral group, like it has a this type of stereochemistry, a specific stereochemistry. Suppose it is H. Wait, I'm just taking it arbitrarily. So when it will get shifted from here, all the conformation of this R group will be same. Like H will be in the plane, chlorine will be above the plane, and OH will be below the plane. Everything will be same. So the stereochemistry of the migrating group just retain. And for this reaction, we require temperature is the vicinity of the 100 degree. So for this reaction, we don't need a vigorous heating or extreme heating. This can happen in the vicinity of 100 degree. So preparation, how this type of acyl azide can be prepared. So the acyl azide intermediate are prepared either by the reaction of sodium azide with a reactive acylating agent, or by diazotization of an acyl hydrazide. So what is, and especially the convenient version of the former process is to treat the carboxylic acid with ethyl chloroformate to form a mixed anhydride, and which reacts with acyl azide anion, and this azide anion will attack here. This azide anion will attack here on this carbon atom, and this will get removed from the system, and we will get this type of acyl azide. And another way to prepare this acyl azide is the if we are in diazotization of the acyl hydrazide. See, when this can be prepared easily from a acyl chloride. This can be prepared from acyl chloride if we added hydrogen type of moiety. We'll get this type of acyl hydrazide, and that after in sodium nitrite with H plus, we know this is a diazotizing reagent. So when we are adding this, we'll get, after diazotize this NH2 will diazotize and give us N2, and we'll get this type of acyl azide. Okay. The reaction can also be carried out. This reaction can also be carried out on the acid using diphenyl phosphoryl azide. So from the acid to prepare this type of acyl azide, we can use this type of diphenyl phosphoryl azide also. See, this type of reagent can also be used. So let's talk about some examples here. So see, I have already shown here the reactant and the product. So how this is happening? So from the explanation, you guys can understand that first what is happening, that it is in sodium plus and N3 minus. So this N3 minus, this azide ion will attack here, and this chlorine will get gets removed from the system, giving us, I am just taking this as a R, so giving us this type of acyl azide, this type of acyl azide. So then after on heating, this group will shift here, and N2 will get removed, and we will get this type of intermediate, this type of isocyanate intermediate. See, I have already taught that this is intermediate, so we can isolate that. If we are not adding any kind of nucleophilic base or any kind of water, we can isolate that as a isocyanate. That will not convert it into any kind of acid or ester. This will be remaining as a isocyanate. By addition, when after trapping that, after collecting the isocyanate, or in the reaction medium, if we already add water or alcohol, then we will get the ester or the acid. Otherwise, we can isolate this isocyanate. Okay. Stop. Then come to the next reaction. In a similar way, the first there is this is a ethyl chloroformate. This is a ethyl chloroformate. So in the similar way, I'm just showing this as a R. I'm taking it as R. So I'm taking the whole group as a R, like from here to here. I'm taking all this as a R. I'm just taking all this as a R. So first it will form this type of diester moiety. Diester moiety. When N3 minus is added, this azide ion is added, this attacks to here, and it get removed from the system, and we get this type of acyl halide. Acyl halide. And on heating, this group will migrate here, and N2 will get removed, minus N2, giving us this type of isocyanate moiety. Giving us this type of isocyanate moiety. And when we are adding water, we'll getting this type of acid. In medium, H plus is there, so nitrogen will take the H plus, and we will get this acid. So in case of this, when acid is get formed, as in the medium already there is a lots of heat, so there is a chance of carbon dioxide elimination. There is a chance of carbon dioxide elimination. Carbon dioxide elimination. So it will give us this amine. It will give us this amine. So now here you can see this is as a NH3 plus. Why? Because in medium H plus is there. So if we consider it as a H plus from the HCl salt, so HCl salt I'm saying. So if we consider HCl acid, then this NH will take this H plus and convert it into the NH3 minus, NH3 plus, and the counter anion will be here. So this is the mechanism. In the similar way, the similar thing will happen. This is thionyl chloride. Everyone knows this thionyl chloride is a chlorinating agent. So first, what will form? This will chlorinate it first. So we'll get the acyl chloride. We'll get the acyl chloride first. Then in the same, when N3 minus will add, then we will get the acyl halide, and in the similar way, we'll get in the similar mechanism, we'll get this product. The similar mechanism. What is happening here? The similar. First acyl chloride will form, then N3 minus will add, then it will get migrate, and it will form this isocyanide intermediate. And if we consider that there is some water in medium, so then it will attack and form this acid, and that will decarboxylate and giving us this amine as a 66% as you have seen. Okay, I think it's clear now. On to the next example. This reagent I have taught already. So this reagent is also been used for that acyl azide formation. In from acid to azide formation, we use this reagent. So this reagent in this formula they use. So what is happening by using this reagent? This acid, you see, there is only one acid group. This is ester. Only one acid group is there. So this acid group will form. If you consider this total group as R, this first it will form this type of acyl azide, then that will get removed and all the migration will happen, leaving us this isocyanate intermediate. Similar mechanism. And here you can see there is a methanol in medium. It is nucleophilic as it is alcohol. Then so the methanol will attack here in the carbon atom. You get this ester as a product. Okay, similar, everything is a similar kind of mechanism. Here the only difference is the azide formation, the reagent is different. You have to remember that this why this reagent has been used. Reagent is used to form acid to acyl azide. You have to remember the reagent, but everything otherwise everything is similar to that. You just form first. You just have to remember the reagent. How whenever you are seeing this type of reagent, what you will do, that you have to find the acid group first, and you have to transfer it to the acyl azide. And if heating is there, then the similar type of reaction, Carbenes reaction will happen. That will remove and will get this type of ester compound. If ester group, if and the main thing is that we have to notice, if this methanol is not there, there is no nucleophilic base is there, then this type of ester will not form. It will remaining as a isocyanate, or if it's water is given, it will form acid and that will remove carbon dioxide and will give amine. But as it is ester is there, so after methanol attack here, we'll get this ester moiety, and see there is no chance of carbon dioxide elimination. So it will remain as a ester. But in case of acid, there is a chance of carbon dioxide elimination. So that will not stop in the acid position. That will go into the further reaction and it will remove the carbon dioxide, giving us the amine. But in case of ester, the reaction stops here in this step. It will not rearrange or eliminate carbon dioxide, because there is no chance of elimination of carbon dioxide. So the next reaction is this one. So in the similar way, see there is a ester group is here. There are two ester group. There are two ester group. So both the ester group are similar. Like see, both are ethyl ester. Both are ethyl ester. So both will react in a similar way. So first there is a 4 carbon inside. So first it will form the acyl hydrazide. In starting of this Carbenes reaction, I already told this will form acyl hydrazide, and this acyl hydrazide on the diazotization by using this one will get the acyl azide. So first it will form acyl hydrazide. This is called acyl. So this will form acyl hydrazide first. And this acyl hydrazide on the diazotization, on the application of this diazotizing reagent, will get the acyl azide. Will get acyl azide. get acyl halide, and on heating, both the in the both side isocyanate will form, and similar kind of as in the medium water is there, so acid will get formed. So in the both side acid will form, both sides this will migrate and giving us this. So on heating, then water will attack. On heating, we will get isocyanate in the both sides. I am not showing that, I have already shown in the many cases. In the both side, you will get isocyanate, and that will, after addition of water, we will get acid, and that will remove carbon dioxide to give this type of amine. And as in medium already H plus is there, so that will get protonated and giving us this as a product. Okay, this is the examples of Carbenes reaction. Just I'm giving 1 minute, just if there is any doubt. Check once the okay, come to the next name reaction, that is Hoffman rearrangement. So Hoffman rearrangement, it leads to the conversion, leads to the, sorry, it will be conversion. It will be conversion. So Hoffman reaction leads to the conversion of acyl So Hoffman rearrangement. This leads to the conversion of carboxylic acid to the corresponding amines with a loss of carbon dioxide. The hypobromide ion reacts to form the N-bromo intermediate, and this is also a concerted process. So what is happening? Just see this first, this amide will react with this hypobromide ion to give N-bromoamide intermediate. So this hypobromide ion would react with this one and give this type of N-bromoamide intermediate, and this N-bromoamide intermediate undergoes this type of rearrangement it will come here and this will shift here and bromine will get removed and we'll get this type of isocyanate intermediate, which after addition of water will get acid, and after removal of the carbon dioxide we'll get amine as our product. Okay, this is similar to the Cartiers. In just the difference is, in case of Cartiers, the leaving group is the nitrogen atom, and in case of this in here, the leaving group is the bromide. Yeah, leaving group is the bromide ion. So now use of NBS in methanol in presence of sodium methoxide or DBU as a base traps the isocyanate as a carbamate. So like in the similar in case of the Cartiers, what is happening, if instead of water, if we use in case of base, nucleophilic base, that will trap the isocyanate and will get this type of carbamate, because instead of acid it will form ester, and that can't remove the carbon dioxide and we will get this type of carbamate as our product. Okay, so the reaction has been useful in the conversion of the aromatic carboxylic acid to the aromatic amines. This will be amines. Amine. N. Aromatic amines. So what is happening? So in similar way, first this Br bromine and KOH will form the hyperbromide ion, and that will react with this amide to give us the N-bromoamide intermediate, and that will undergoes the rearrangement, giving us this type of amine. The similar kind of reaction will happen. First, see, I have already shown here. First, this hyperbromide ion will form, it will attack, and it will form this N-bromoamide, and that will rearrange to give us this type of isocyanate. And on addition of water, we will get ester that will remove carbon dioxide, and we'll get the amine. In the similar way. So direct oxidation of amide also can lead to the Hofmann type rearrangement with formation of amine or the carbamate. One reagent that is used is the lead tetraacetate. So what is happening here? So first, if we use any kind of oxidizing agent, so this type of amide can be formed, or the amine or carbamate can be formed. Hofmann type of rearrangement will happen. On the addition of this lead tetraacetate, this type of similar kind of rearrangement will take place, and we'll get this type of the similar product we get in case of Hofmann rearrangement we'll get here. So this is called Hofmann type rearrangement. Okay, see, similar kind of product we are getting as we get in Hofmann rearrangement. So this is called Hofmann type rearrangement. So the next is Smith reaction. The carboxylic acid and the esters can also be converted to amine with the loss of carbonyl group by the reaction with hydrazoic acid, which is HN3. So carboxylic acid and esters can also be converted to amine. See, the carboxylic acid or ester converted to amine. The similar kind of reaction in every case, the carboxylic acid is converting to the amine, but through a different kind of reagent. So here the reagent is hydrazoic acid. So an azido intermediate is get generated by the addition of hydrazoic acid to the carbonyl group, and this is called azido intermediate. Azido intermediate is formed by the addition of the hydrazoic acid and the migrating group. When this group get migrate, the stereochemistry is written as similar to the Cartiers and Hofmann, and we'll get, after removal of the carbon dioxide, we'll get this type of amine. So the reaction with hydrazoic acid converts ketone to amide. in case of acid, it converts acid to amine. But in case of if we using the same hydrochloric acid in case on ketone or amide, ketone, then it will form amide. So what is happening? The first, this N3 minus will attack here and will form this type of alcohol will get formed, and there is a chance of rearrangement. See, this N minus will go here and OH get removed from the system. There is a chance of rearrangement. Also, if we see rearrangement, as we skip the rearrangement also, there is a, if the in the medium is already is acidic, then we'll get this compound, and this OH comes here, and this R group shifts to this nitrene nitrogen, and this N2 will get removed, and we will get this type of amide as our product. Okay. In case of acid, what is happening? There is already OH group. So after the formation of this amide, there is a in this side there is a acid. So this acid will decarboxylate and will get amine as a product. But as this is ketone, there is instead of OH there is a R group. So there is no chance of decarboxylation. So in case of ketone, we will get amide as our product. This is called Smith reaction. So Smith reaction, what is giving? In case of carboxylic acid or ester, will get amine, but in case of ketone, will get amide. So this is the mechanism. Okay, I think it's clear to everyone. I'm just giving 1 minute to check once. Okay. So let's shift to the next slide. So the unsymmetrical ketones can give mixture of products because it is possible for either group to migrate. So in case of unsymmetrical ketones, we can get a mixture of product because see there is a 2R group in the both sides of the carbon. So this can after formation of this azide, after formation of this, when it comes here, this can also shift here, giving us this as a product, and I'm showing you the different color. When this shifts, we get this as a product. Okay, so in case of mixed unsymmetrical ketone, we can get mixture of product. So both the inter and intramolecular variants of Smith reaction in which an alkyl azide affect the overall insertion have been observed. So what is happening here? So alkyl azide, first this minus will in a similar way to attack here in case of what is happening in case of ketone. So we'll get we'll get this one. So then in a similar way, this will come here and this ring bond will migrate into it and we get this as our product. So there is a chance of ring expansion. So there is a lactone kind of thing, is lactam kind of, from ketone we are forming lactam. A cyclic amide is called lactam. A cyclic amide is called lactam. Lactam will form. Okay. In a similar way, there is also this is intermolecular because this reagent is attacking this ketone from the outside. But what in this the difference is that this is intramolecular. This is already in the molecule. So intramolecularly it will attack here, and it will attack here, and similar kind of reaction will happen. A similar kind of reaction will happen. This is only this is inter, but this is intra. But this is intra. Okay. These reactions are especially favorable for beta and gamma hydroxyazides, which can proceed through a hemiketal intermediate. So, see, when this type of ketone is when alcohol azide is there, so alcohol group will first attack here and will get this type of compound, which is gamma or beta hydroxyazide. So there is, if where is my cursor? So first it will attack here, then in the similar way this will come, this in the similar way will get this type of azide. When this O minus comes here and N2, this N2 will get removed from the system and will get ring expanded form. So as O oxygen is plus, so this bond get broke, and in medium OH minus will attack here. Okay. Only there will be, sorry, this arrow should be this side. This arrow should be this side. If plus is on the oxygen atom, this will break, attack here, and this will get break. Okay. So let's solve one of the example. Just note it down. So we'll solve it together. So in the similar way, what will happen when this azide is there? N3 minus will, phosphoric acid is here. So in presence of acid, I'm taking this whole group as R. This whole group as R. So what will form from here? In presence of azide, in presence of acid, we'll get this type of acyl azide, and then it will take place in Cartier rearrangement, giving us this type of isocyanate intermediate. And acid, as acid is there, so we are considering that in medium some water will be there, because we know most of the acid are condensed into water. So we are assuming that some amount of acid water is already in medium. So then that water will attack and we'll get this ester kind of acid kind of moiety. Which undergoes decarboxylation, giving us this amine, and acid medium acid is already there. So this type of rearrangement will happen, leading us to this amine as our product. Okay. Now next reaction. This is also similar kind of reaction. Acid is there, Na3 is there. So I'm not showing again and again. So similar kind of this RCON3 will form. I'm just showing the intermediates only, because mechanism I have shown several times. So this type of acyl azide will form, and this will give this isocyanate, as it is acid. We are considering some amount of water is there, and by removal of carbon dioxide plus H2, we'll get acid, and when acid carbon dioxide gets removed, we can get this as our product. Okay. So the next reaction, similar kind of a, this is called trifluoroacetic acid, TF. Okay, this is stronger acid than acetic acid. Why stronger? This is not just general chemistry question. Why stronger acid? Because this conjugate base is more stable than acetic acid. What is conjugate base? After the removal of the H plus, which when acid removes one H plus, the anion we get, this is called conjugate base. This is called conjugate base. So this conjugate base is stabilized through resonance, that is similar to the acetic acid. In case of acetic acid also, the conjugate base is stabilized by the resonance effect. But also here there is an extending effect, that there is a 3 fluorine atom, and fluorine atom has a minus I effect. So this CF3 has a strong minus I effect. CF3 has a strong minus I effect. So the negative charge get delocalized. So this conjugate base is more stable than that of this CH3 atom, because whereas the CH3 has a plus I effect, that will push the electron density towards the carbonyl, but there is a minus, so it will pull the electron density. So this one is more stable. So this conjugate base is more stable. conjugate base is more stable. Okay, that's why it is more acidic. So this is just for basic knowledge. So when this N3 will attack here, in the similar way N3 will attack here, we'll get a O minus, and this, then this ring bond, this will come here, and this ring bond will get shifted to this nitrogen, and this N2 gets removed, and we'll get this as our product. Okay, this bond is getting shifted. This bond is getting shifted. This one. This bond is getting shifted. Okay. Next is loss and rearrangement. This is a similar kind of rearrangement I was talking about. Like I have already taught Cartier, Hoffman, Smith. So next is loss and rearrangement. So in every, like, all the reactions are almost same because the intermediate is isocyanate. See, you if you go in the previous slide, you can notice that in case of all the reaction till now I have taught in all this reaction, the intermediate is the isocyanate. So all the reaction, we can compare all the reactions are comparable. The only difference in all the reaction is the leaving group. In case of Cartier's, the leaving group is the N2 atom. In case of Hoffman, the leaving group is the bromide ion. In case of Smith, the leaving group is the N2, but the addition is happening directly to that, but in this case, the difference between Cartier's and Smith is that in case of Cartier's, the N3 minus the azide ion is attacking, and but in case of N3 minus is reacting with the acyl chloride, but in case of uh, Smith reaction, the reaction is directly taking place with the acid. So there is an advantage of Smith reaction is that we do not need to acylate do not need the acylation of the acid. It's acylation of the acid, like chlorination. We don't have to form the acyl chloride from the acid. We can directly form amine from the acid. But in case of Cartier's, we need to form the acyl chloride first, then that will react with the azide ion. So in case of loss and rearrangement, the similar type of reaction is happening. So first, see, there is a hydroxamate ester is there. So this is called hydroxamate ester. So the hydroxamate ester is transferred the corresponding amine by the loss of carbon dioxide. Every time I am saying that if this is acid, there will be loss of carbon dioxide, and this is also a concerted process. So what first is happening? See, there is a OH group. So there is as a living group there is a OH. So we all know that OH is a bad living group. OH is a bad living group. So first, to make it a good living group, we have to activate. So first, what is happening? So this esterification is happening. This will attack to this one of ester compound or something. It will form a ester. Then it get this OH get transferred into a good living group. Then this lone pair comes here, and this bond will shift here and shift to this nitrogen atom, and it gets removed from the system, giving us this isocyanate. And on addition of water, we'll get acid first. It will get we'll get acid first, and that will eliminate carbon dioxide, and we'll get our desired amine as our product. So minus CO2 is happening, minus decarboxylation is happening. Okay, so see, all the reactions are same, just the difference is the leaving group. Cartiers, the leaving group is N2. In case of Hoffman, the leaving group is bromide. In case of Smith, the leaving group is again N2. And in case of Lawson, the leaving group is a hydroxyl group. The leaving group is a hydroxyl group. So let's talk about an example. So see, there is a double amide, double hydroxamate ester is there. So what one of these will react? So one of these will react with this amide, giving the OH. This is the activating agent, and this OH will transform it to good leaving group, and this will come here. And OH get removed from the system, and we will get this type of isocyanate as an intermediate. So usually, if there is a any solvent like water or alcohol, that usually attack to this isocyanate. But we all know that intramolecular attack is always favorable over intermolecular. Intermolecular attack is always favorable over intermolecular. Okay, so when so see here, already there is a internal nucleophile is there. So instead of water, this nitrogen will attack to this carbonyl atom and giving us this diamide complex, and this diamide complex again when water atom diamide complex, and this diamide undergoes hydroxylation, this water attack here and here, will get this type of this as our product. Okay, so here what is happening, intramolecular attack on the isocyanate intermediate is happening. Usually water or ester attack, whereas there is a intramolecular attack is possible. So before water or any solvent atom attack, this internal nucleophile will attack and giving us this product. Okay, so our next name reaction is the Beckmann rearrangement. This is called Beckmann rearrangement. So another important reaction involving migration to the electron deficient nitrogen is the Beckmann rearrangement, in which oxygen are converted to the amide. So what is the difference from the past 4 reactions, I guess? Cartiers, Hoffman, Lawson, Smith. So what is the difference from the last 4 reaction is that this reaction is happening from the oxygen. See, this is called oxygen. When carbon, there is a double bond between carbon and nitrogen, and as a OH group is attached to the nitrogen, it is called oxygen. This is called oxygen. This is oxygen. Okay, so oxygen is converted to the amide. So properties: if variety of protic acid, Lewis acid, this is Lewis. You have protic acid, Lewis acid, acid anhydride, acyl halides can cause the reaction to occur. The mechanism involves the conversion of the oxime hydroxyl group to a leaving group. So by this protic acid, Lewis acid, acid anhydride, acyl halide, all are used just to convert this bad living group OH to a good living group. It's a bad living group because it's not resonance stability. It don't has any resonance stability or anything. It's a bad living group. So to make this a good living group, all these reagents are used. So ionization and migration occur as a concerted process. So when this ionization, like this oxygen is this OH group is turning into a good living group, and this bond will shift, and this migration and this removal of this OH all happens in a concerted process, and the anti to the oxygen living group migrates. See, so there is a arrangement. The OH, this bond, so usually that bond shift which is anti to this bond, N oxygen bond, which is anti. See, if we show with this color, another pen. So the bond which is anti to this OH bond. So see, among these two, this bond is anti. So this has been shifted. So this has been shifted because this is anti. This is anti. So anti arrangement is required. This is one of the important point of the Beckman. So if nothing matters that which is but if which is more if there is no stereochemistry it's written, so you have to consider the more migrating aptitude, which group has a more migratory aptitude that will migrate. But if there is a stereochemistry of that N oxygen bond, so you have to consider the anti arrangement. So that bond will that group will migrate, which is anti to the OH group. If there is not shown as a there is no bond is shown in between the nitrogen and oxygen, you can migrate that group which is which has more migratory aptitude. So what is happening? The migratory group retains its stereochemistry. Like the previous reactions, all when this R group will shift, the stereochemistry of the R group will be retained. So the migration results in the formation of the nitrilium ion, which captures the nucleophile. Eventually, hydrolysis leads to the amide. So there is the mechanism is elaborately shown here. So what is happening? First, OH group gets activated. How it will get activated? By this protic acid, Lewis acid, acid anhydride, and acyl halide. By all these things, this OH group get activated. See, it becomes a good living group. Now this is a when it was as a OH, it is a bad living group. Bad living group. But when some activating agent is added, it becomes a good living group. So it tends to get removed from the system easily. It's a good living group because there is a positive charge on the oxygen atom. So after removing, this can be neutralized. So this is a good living group. So what is it? This bond is anti to this bond. These two bonds are anti. So which of the bond will shift? This one will shift. This one will shift. And this type of a transition state we can imagine. This is a transition. Why transition is this not has been isolated. This type of transition state can be seen, and so this will shift it, and there is a charge of the nitrogen atom, and then which will attack here. Which will come. Nitrogen get neutralized, and we get this type of intermediate. It undergoes tautomerism, giving us this amide as our product. Undergoes tautomerism, giving this as our product. Okay, so let's solve some examples based on this Beckman rearrangement. So what will happen here? So HCl is there, HCl or acetic acid, what you can consider as a. So this acid will protonate one of this OH atom, and it gets OH atom, and it will be OH2 plus. And we all know removal of water is always a favorable process. So there is the chance of removal of which water molecule. So see here, there is no stereochemistry has been shown. There is no stereochemistry of NO bond. There is no stereochemistry of NO bond. No stereochemistry no stereochemistry of the NO bond. So that's why we can't consider the anti-arrangement, because we don't know the stereochemistry of the NO bond itself. So how can we imagine? How can we find the anti-arrangement? So that's why we have to go for the way we used to migrate in the some previous reaction we have done, like pinnacle arrangement or something. So we will just go for the most migratory aptitude. So we all know that aromatic groups, aryl groups always have a greater migratory aptitude than that of the aliphatic. So this bond will get migrate. So this phenyl group will migrate and giving us this as our product, because migratory aptitude of aryl group is greater than alkyl group. So that's why this phenyl will get migrate. Okay. So a fragmentation reaction occurs if one of the oxime substituents can give rise to the relatively stable carbocation, and this is very likely to occur if the X is a nitrogen, oxygen, or a sulfur atom. So what are they saying? So usually we have seen there is a migration from the carbon at R group to this carbon to this nitrogen atom. We have seen there is a migration of the R group from carbon to nitrogen atom. But here there is no the bond group will not migrate. That this bond will get broken, and this living group will get removed from the system. When this is possible, when there is a chance of formation of a stable carbocation, when there is after the bond breaking, if there is a there is a chance of formation of stable carbocation, because there is a any adjacent electron donating group which can stable this carbocation, then this bond get removed, because after the removal there is a positive charge, so that has to be get stabilized. So when there is a adjacent oxygen or any heteroatom which can stabilize this carbocation, this type of reaction happens. So here this is one of the example why this is why after this PCl5 will this O minus will attack to this phosphorus atom, and this bond will not migrate. Instead of migration, it will just break. Instead of migration, it will just, this will not happen, this will not happen, it will just break. It will just break, and this will get removed. So in medium, what is we are getting? medium we are getting carbocation and a carbon nitrogen triple bond. So you can you may thought that you may think that here I have seen written that the X has to be a nitrogen, oxygen, or a sulfur atom. X has to be a nitrogen, oxygen, or a sulfur atom to stabilize the carbocation. But see, there is no heteroatom adjacent to this. There is no heteroatom adjacent to this carbon. How this carbocation is getting stabilized? How this carbocation is stabilized? So you can notice that this is a tertiary carbocation. This is a tertiary carbocation. Plus, not only tertiary, it is a benzylic carbocation. This is see, there is a benzene ring, so it is 3 degree tertiary plus a benzylic. So we all know benzylic carbocation is highly stable because of the resonance stability through the benzene ring. So it is 3 and tertiary carbocation is also stabilized by the hyperconjugative effect. So this benzylic plus 3 degree. 3 degree is stabilized by the hyperconjugative effect, and the tertiary carbocation, the benzylic carbocation is gets stabilized through the resonance effect. So so that's why it is highly stable. So this is stable, highly stable, and then a elimination type of E1 type of reaction takes place, which is this one of the each atom gets broken, and we get a alkene. This kind of E1 elimination kind of takes place, not E1 actually. This type of elimination takes. So this type of elimination take place, and we'll give this type of alkene as our product. Okay, understood? Let's talk about the next section. These are the all example of Beckmann rearrangement. So see here, in none of the cases the stereochemistry has been shown. In the none of the cases, so there is no stereochemistry, no anti effect, no anti, no anti effect, because there is no stereochemistry. So we have to consider the migratory aptitude. We have to consider the migratory aptitude. So among the CH3 and normal alkyl bond has more migratory aptitude. So see, we have to see the what is the adjacent, just adjacent. So we can sometimes we make a mistake and see that we shift this ring bond. We may think that this is a ring expansion will happen, but no, see, this is not connected to the ring bond. There is another bond. So which will shift? This bond will shift. This bond will shift. Okay, see, this bond will shift, and totally we will get this type of amide. Okay, but here this is directly connected to the ring. Difference between these two, just notice, this is not directly connected to the ring. There is a bond, so that bond will get shifted, but it is directly connected to the ring, so there will be ring shifting. And which side the ring will get shifted, because there is a allyl group is here. So as there is a aryl group is here, due to this presence of this aryl group, this bond will get shifted. This bond will get shifted to this nitrogen atom and always get removed. And after this removal, there will be generation of plus charge, and then in this acid, as it is acid, so in medium if we consider water is there, so that water will attack in this position, and then it is going to undergo tautomerization. When we get this amide as our product. Similar kind of mechanism I've already shown in, as this structure is too big, I'm not showing here, it will be too congested. So I think everyone has understood, because the similar kind of mechanism is happening. Just if bond will shifted, there will be a positive charge, and that water medium, as medium is acidic, so water will attack here, and this will undergo tautomerization and giving us this amide as the product. And here also, here see both the bond are similar, so any bond can be shifted. Both the bond are in similar nature, so any bond can shift. Then water will attack. Water will attack in this position, and we'll get this as our okay. So this was the all I have all the reaction based on nitrene till now. This is all the reactions of nitrene. So I think these are enough to learn about the nitrene, or I think if you go through all the name reaction here I have shown what is first one is Cartiers, then Hoffman, then Smith, then Lawson, next then the last one is the Beckman rearrangement. If you go through these 5 rearrangement, I think you can solve all the problems based on nitrene. So just these are enough to solve any problem based on nitrene. So just go through these problems properly. Just try to learn the stereochemistry, and the major thing I have highlighted again and again, that when this shifting happens, the stereochemistry of the migratory group is retained. The stereochemistry of the migratory group is retained. This is the one of the major thing to be noticed. So you have to consider that, and I think this much is enough to have based on the nitrates. So here I am just that's today is the last session. So just for a recap, or for making just for a recap, I have given some exam problems which I haven't. I have taken the problem. So let's solve together. I will show them. So just for a quick recap, you guys can also just check that if you have remembered everything or not. If you are not able to solve the problem, just go through the previous slides, previous lectures. uh, both the first two lecture both the lectures and have been uploaded in the YouTube also. You can go and check there. The third lectures will be uploaded soon, and today's lecture will be uploaded also. So you can go through that also if you having any problem, because after this session I won't be able to contact you or connect to you guys. So if you are having any doubts uh, regarding my sessions and regarding my slides also, you can ask there, or you can ask there, you can comment there, or also if that you can so I will try to clear your doubts or anything there. So if you are, because I will not be able to connect to you guys after today. So if you are having any doubts or anything I have done, or if you are noticing any mistake what I have done, you can tell me about that also. So that though both the videos are available in YouTube, and I have also uploaded the slides in the Google form. You can check from there also. So those, I think NPTEL will give you the access to check those. So that's much. So let's solve this problem. I have 30 minutes left. So let's solve this. I think this all these things I have been already taught. I just for a recap. So what will be the product here? So this is chloroform, and when chloroform is react with a NaOH base or something, it will give us the carbene. What type of carbene it will give? It will give this carbene. Give this carbene, and that will give a in addition product. Addition product here. Okay. So many can ask, what is this? What is the role of this reagent? NaOH and chloroform will form this carbene, and water is a solvent. What is the role of this reagent? So this is a phase transfer reagent, which is called PTC, phase transferring catalyst, which is called PTC. So why PTC? What is the work of phase transferring catalyst? If we were doing some reaction in water and we have some reagent which is organic, which is not water soluble, so if by using phase transferring catalyst we can make them react. See, the sodium hydroxide will get dissolved in water, but the chloroform will get dissolved. The chloroform is organic, that will not dissolve in water. So how NaOH and chloroform will come together and uh, giving us this carbene? The proportionality of reaction will be too small because there will be a solubility problem. Chloroform will not go into the water and NaOH will be into the water. So there will be a solubility problem and the probability of reaction will be too small and the yield of the product will be too less. So by using the PTC, that is phase transferring catalyst, we can make the both phase transfer, like both the chloroform is in a different phase and the NaOH is in a different phase. By using the phase transferring catalyst, we are making them come closer and react with each other and giving us this carbene. Okay, so this is the role of this catalyst. This is the phase transferring catalyst. It will just help the reagent from the different phase to come together and react to give this type of intermediate, this carbene intermediate, which will added to this alkene bond. Okay, the next is uh, this is also a base, so this will form this carbene. We all know that fluorine bond is stronger than chlorine bond, so fluorine bond will be there, only chlorine bond will get removed and will give this as a product. Okay, next is this one. This is also a carbene generating reagent. I have already taught all this in the first session maybe. So this will give this carbene. And that will add it to this. Okay. Now the next one is this one I have already taught you. What type of reaction is this? This is Bomford-Stevens. When this you will see this kind of tosyl azide is there, tosyl hydrogen is there, and there is a weak base. This is called Bomford. If anyone who has missed the first sessions, first two sessions, I have explained all these in the first two session maybe. So go there and check. This will give a clear view and what is the mechanism, because here I can't show the mechanism. So what will happen? This will generate a carbene here, and this carbene will insert into this double bond, giving us this as our product. This will get insert into that double bond. So this will be our product. Okay. If anyone wants to know the mechanism, just go through the previous lectures or previous PPTs I have already shared, so you can understand. The videos are already uploaded in the YouTube. First two, third one will be uploaded today or tomorrow, most probably, and this one will also be uploaded along with that. I was busy in these weeks quite, so I couldn't. So what will be the product here? So this is diazomethane. So when there is acyl chloride and diazomethane, what type of reaction is this? This is called Wolff reaction. This is called Wolff reaction. Okay. I think this one was also I have taught already. Called Wolff reaction. So first it will form, and I'll not show the mechanism here. I will just draw the product. First it will form this. First it will form this, then form this one. We will get this as our. So the interesting thing is here, as there is no nucleophilic solvent, so this reaction will stop at this place. The reaction will stop at this place, as there is no nucleophilic solvent to convert into it any acid or ester. So this will stop in this place. So this is what type of reaction is this? Just try to today I have taught you guys this. This is Beckmann rearrangement. This is Beckmann. When there is a oxime kind of intermediate, oxime type of substrate is there, just go for the Beckmann rearrangement. Just think about Beckmann rearrangement. I'm not saying that always it will be Beckmann rearrangement. Just think about the Beckmann rearrangement, then go for, then check if this is possible or not. Therefore, the first thing you have to think is Beckmann rearrangement. So what is happening here? This can be act as a base. So what this will this and see there is a stereochemistry is shown. So the with this bond, this is anti, this is anti. So this, in case of here, see this is a 6-member ring. So see there is a this is a 6-member ring. So if it get migrate, there will be formation of 7-member ring. A 7-member ring is not that much stable, but there is another probability which is more stable than that of the bond shifting. So if this bond get just broken, and that gets removed, what will get? We'll get a triple bond here. Sorry for the structure. We'll get a triple bond there. There will be, I am showing this as a R group. There will be a plus charge because that bond got broken. And there is a, I'm just showing as a SiR. Okay. So you all know positive charge beta position to the silicon atom is always stable, because this silicon has a tendency to get carbon silicon has a tendency to get broken, and there is a chance of formation of stability. So this bond is always there. The beta position, positive charge beta position to the silicon atom is always stable. So beta to silicon is always favorable. Positive charge beta to the silicon is always favorable. So this bond get broken, and we'll get this as our product. Okay, I am considering this as a R dash. I am considering this as a R dash. Okay, and the next reaction, a similar kind of reaction will happen. What is it? This thionyl chloride will add it to chlorination. So this will get chlorinated. Will form. So there is no stereochemistry, so we can just consider. So this will get removed. So we'll in the medium will form then it is in medium Cl minus is this is there is a chance of in medium Cl minus is there. So in medium Cl minus will attack here this carbon atom. Carbon atom leading us to this one. Okay. Next is benzene condensation. So why you guys are thinking why benzene condensation? So in case of the in normal benzene condensation, what is the mechanism? We know that this is all you have been taught in your graduation already maybe. So when in case of benzene condensation, the Cn minus graduation or plus 2 I guess. So benzene in case of Cn minus is added. So here first Cn minus will act as a nucleophile. So first Cn minus will attack here and this will get open, giving us this. Giving us this. Then this OH will deprotonate the H and giving us this. Okay, there is a minus charge here. This minus charge will attack another molecule of aldehyde, giving us this type of intermediate. When O minus is there, and as in medium water, so O minus will get protonated and you will get this. So this type of intermediate will form. Then there is a rearrangement will possible. So what will happen? This OH bond comes here and this Cn minus gets removed from the system. Okay, this Cn minus, see what is the deprotonate and this comes here and we will get this type of alpha hydroxyl ketone moiety. Alpha hydroxyl ketone moiety. Okay, this is the normal benzene condensation reaction. So this type of similar, but the drawback of this reaction is the drawback is the Cn minus is highly toxic. This is highly toxic. So this is the major drawback of this reaction, because cyanide is highly not only toxic, it is fatal also. Like you can take anyone's life. So it is highly toxic. So use of Cn minus is highly dangerous. So as a substitution, uh, reaction has been introduced, which is NAC catalyzed benzene condensation. NAC means the N-heterocyclic carbene. NAC means N-heterocyclic. This one I have introduced this name in the first session. You can go there. I have introduced this name in the first session. What is what is N-heterocyclic carbene? N-heterocyclic carbene. In a short form, it is called NHC. NHC. Okay. So what is happening? This type of moiety is called N-heterocyclic carbene. So what is happening? This type of N-heterocyclic carbene. See, this is a carbene. Why N-heterocyclic? Because in the heterocyclic ring is there, while nitrogen is there. So these type of carbenes are highly stable. Stabilized because of this adjacent nitrogen atom. Because this is a singlet carbene and there is a vacant p orbital which can be stabilized by this electron donating of this nitrogen atom. So it is highly stable. So this type of carbene can be uh, prepared and stored in laboratory. So it is highly stable, and in case of uh, in case of diazomethane or something, where when the carbene is generated, it have to be generated in the medium. We can't store that. But this type of carbene are so stored, we can store that in laboratory. So highly stable. So this type of carbene will attack to this carbonyl atom, then O minus will form. This is but like this is this NHC has been using as a substitution of the Cn minus. So when this O minus will form, then this proton get deprotonated from by this O minus. It will take the D atom, and this minus will get, there is a chance of resonance stability here. So then it will attack to the another benzaldehyde. Then it will attack to the, it will come here. It will attack to the another benzaldehyde atom and will form this type of intermediate. And in a similar way, this O minus comes here and the NHC gets removed from the system, and it can take part into the next molecule. So it is as a catalyst, so we can regenerate in the medium and we get this type of alpha hydroxy product as our desired Okay, we are getting alpha hydroxy as our desired product. So what is the advantage of this reaction over normal benzene condensation? The advantage of this reaction is this is an organocatalyst. See, all the molecules are organic. There is no metal, nothing has been used. So everything is organic. So it's organocatalyst. Anything which is not metal is good, is comparatively greener for our environment. If metal, because we know to decompose a metal or something, our art takes a lot of time. But when it is organic compound, this has been formed. This can be consumed by our nature automatically. So this is organic. So it's an organic catalyst, and we all know that it's a organic catalyst has been a very interesting topic nowadays, because last year the Nobel last not in last year 2021, the Nobel Prize was for this organocatalysis, because this is a very important like emerging topic right now, because this has a huge application for, and it has a huge application, and there is a huge chances to discover on this topic. So in 2021 it got a Nobel Prize. The Nobel Prize was given on this organocatalysis. The Nobel Prize was given on this organocatalysis. Okay, so this type of thing is happened. So this is the substituted of the benzene condensation. And the another important thing about this type of NAC catalyzed benzene condensation, that enantiomer selectivity can be generated just by using a chiral NHC. Just by using a chiral N-heterocyclic carbene, we can generate a chirality. See, by just using a chiral NHC, by uh, using a chiral, where there is a chirality in here or here, we can generate a chirality in the product. By using chiral NHC, we can generate the chirality in the product. So it is highly important nowadays. So next is the acidination. So direct preparation of an aziridine from the alkene is possible by reaction of the alkene with a nitrene or a metal nitrenoid species. Nitrene can be generated thermally or photochemically from the azide. The metal catalyzed reaction of the nitrenes with the alkenes has received considerably studied, and the variety of metal catalysts can be used with the copper 2 salt being the most popular. As an example, you can see the styrene was converted into N-tosyl aziridine N-tosyl aziridine by the reaction with N-tosyl aminophenyl iodine with copper 2 triplet, we can get this type of N-tosyl aziridine. So as a reagent, the N-chloramine T or N-bromamine T can also be used. So here I have shown some example. An alternative to an metal salt is the use of a source of bromine as a catalyst. So why this is happening? Instead of here we are using metal catalyst. So alternative, by just if we stop using metal catalyst, just by using a brominating agent, this type of brominating agent, we can we can substitute the use of the metal salt. We can substitute the use of the metals and we can form this type of aziridine moiety just by using this type of brominating agent. So in this case, the aziridation of tert butyl cinnamate 73 occurs highly enhances selectivity with the copper triplet and the bioxygen ligand. So in just written twice. By this type of reaction can happen in enantiomer selectivity also, because by using a enantiomer selective ligand we can form this reaction through a enantiomer selectivity. Okay, the same similar, just a simple aziridine formation like the epoxidation. So here is the summary of the main relationship between the carbene and this other compound. When a nucleophilic compound is added to a carbene, we get a carbanion. Nucleophilic you get a carbanion. We get a carbanion. When a neutral species is added, we get a ylide. When a neutral species is added, we get a ylide. When a radical added, we get a radical. When we just heat or if when a base is added, we get a carbocation. When a base is added, we get a carbocation. Sorry. Okay, so this type of compound is this carbene reacts with different type of compound in like this way. This is the summary of the reaction type of carbene. Okay, so today is my last session. So thank you everyone for listening to my session till this 4 weeks. So for by teaching you guys, I have learned a lot of things about, like I have explored. I got a chance to elaborate or to freshen up my knowledge on the reactive intermediate. So it was a great opportunity for me. Thank you NPTEL also for giving me this opportunity. So if I get a chance, I will try to teach some new topics in the in your next semester session. So thank you everyone and all the best for the exams. And before that, I will upload all the videos and slides, so you can go through that and just log the exam, so that make a good score. And if while studying my videos or anything, if you are having any doubts or anything, just try to contact just to I have already uploaded in the YouTube, so you can comment there, so I will try to explain whatever your doubts are there, because after this session I can't contact through this uh, online session, so you can comment me there, or I will upload the slides. Thank you everyone.